Welcome to This Explainer. Today, we're doing something pretty incredible. We're actually bridging a massive 200-year gap in physics. We are going to start with these foundational macroscopic wire experiments from way back in the 19th century and then shrink all the way down into the invisible vacuum of the atom. We're going to explore how classical electromagnetism, the physical forces that were defined literally centuries ago, might just hold the answer to a foundational atomic mystery that still perplexes us today. It's going to be a fascinating journey, so let's just dive right in. So let's start with the ultimate electrostatic paradox. Think about this for a second. The positively charged nucleus and the negatively charged electrons should, theoretically, pull straight toward each other, right? I mean, opposite charges attract. That means the atom should violently implode in a fraction of a second. But it doesn't. Atomic volume remains mostly just a stable, empty vacuum. So what exactly is the invisible scaffolding keeping it propped open? Well, to figure that out, we need to rewind a few centuries and look at the actual physical rules governing charge and motion. The entire foundation of electrodynamics was laid down through a really rapid series of brilliant breakthroughs. Back in 1820, Hans Christian Ørsted and André-Marie Ampere first sparked the field. They discovered the strict physical connection between electrical currents and magnetism. Then, skipping ahead to the 1860s, James Clerk Maxwell mathematically unified those ideas into his famous equations. But, to be honest, the math detailing how these forces acted on moving charges remained kinda messy. Actually, the brilliant J.J. Thomson literally made a fraction error, a factor of 1/2, when trying to calculate this dynamic in 1881. It took Oliver Heaviside in the 1880s to step in, correct it, and refine the math using vector notation. And finally, in 1885, Hendrik Lorentz nailed down the modern relativistic form that we still rely on today. Okay, so to understand the atom, we first have to understand Ampere's force law. Think of these as the rules of the wires. See, back in the 1820s, Ampere wasn't looking at subatomic particles at all. He was conducting these really meticulous experiments with tangible, current-carrying metal wires. He was measuring the physical push and pull when electricity flowed through them. He was basically mapping macroscopic forces, figuring out precisely how moving charges create magnetic fields, which then interact with other moving charges nearby. And the physical behavior of Ampere's law is just absolutely fascinating. Best of all, we don't even need dense math to grasp it. Picture two parallel wires. If the electrical current is flowing in the exact same direction through both of them, they create an attractive magnetic force. They physically pull together. But, and this is key, if you flip the current in one of those wires, so they're flowing in opposite or anti-parallel directions, they create a repulsive force. They violently push away from each other. Seriously, keep this specific mechanism locked in your mind because it is absolutely crucial for where we are heading next at the macroscopic level. Let's just take a quick moment to consider this exact number, 2 × 10⁻⁷. Why does this matter? Well, this highly specific wire formula historically defined the standard unit of electrical current itself, the ampere. By strict definition, 1 ampere of current is exactly what it takes to produce 2 × 10⁻⁷ newtons per meter of force between two parallel wires positioned exactly 1 meter apart in a vacuum. To put that into perspective, it's a profound realization that such a fundamental standard of modern physics wasn't initially defined by, say, counting invisible electrons. No, it was defined by measuring the tangible mechanical force of metal wires pushing on one another on a laboratory bench. But, of course, to get to the atom, we have to transition from Ampere's macroscopic wires to Lorentz's microscopic particles. The Lorentz force law is kind of the ultimate unifier here. It takes the electrostatic forces, which is just the simple pushing and pulling of stationary charges, and it perfectly blends them with the magnetostatic forces of moving charges into one incredibly elegant mathematical law. It basically dictates exactly how a single isolated particle behaves when it's flying through a combination of electric and magnetic fields. Now think about how we deconstruct the Lorentz equation physically, because there's a really stark difference between its two components. The electric component, it doesn't care at all how fast a particle is moving. It just pushes it, changing its kinetic energy directly. But the magnetic component is entirely dependent on velocity. And here's where we find one of the most beautiful quirks of physics. The magnetic force dictates its push via the right-hand rule, and elegantly, it does zero work. That means it cannot speed a particle up or slow it down. It only changes the particle's direction. Think of it like a steering wheel, not a gas pedal. And this steering wheel analogy brilliantly illustrates why the Lorentz force is so powerful. Because it acts perpendicularly to the particle's velocity, it continuously forces particles into circular paths. This is what we call cyclotron motion. It's the exact same math that governs how particles are trapped in penning traps in laboratories, how we steer high-energy beams in massive particle accelerators, and even how charged particles from the sun spiral through the Earth's magnetic fields to create those stunning auroras. Plus, the whole thing is a fully relativistic framework. That means it holds up beautifully even when particles are traveling at near light speeds. All right, so let's dramatically zoom in from that macro world of wires and auroras right down to the atomic scale. We're back at our microscopic mystery. How do these classical rules, Ampere's pushing wires and Lorentz's steering particles, actually apply to the internal structure of an atom? We already know the electrostatic Coulomb force is relentlessly trying to crush the atom, constantly pulling the electron and proton together. So where is the pushback coming from? What mechanical force is robust enough to counteract that implosion and maintain the vast emptiness of the atom?
Well, this brings us to a really fascinating application of the source material we're exploring today, the Rihan Atomic Model, or RAM for short. The RAM framework synthesizes everything we just covered to resolve this exact atomic volume mystery. It proposes that the atom achieves what it calls mandatory electromagnetic equilibrium, or MEE. And here is the kicker. It achieves this stability not through some bizarre, unknown quantum force, but by strictly adhering to the exact classical electrodynamic laws we've just been talking about.
Let's walk logically through this analogy step by step, because it's pretty brilliant. In this model, think of the orbiting electrons and protons as moving charges. When they counterorbit, meaning they are spinning in opposite directions, they act exactly like Ampere's wires. They create an effective anti-parallel current. And what did Ampere's law tell us about currents moving in opposite directions? Right, they violently repel each other. This brings us to the absolute elegance of this whole symmetrization. Think of it as an atomic tug of war. On one side, you have the electrostatic Coulomb force desperately trying to pull the atom together and collapse it. But counteracting that, because those charges are moving in opposite directions, the Ampere and Lorentz magnetic forces are violently pushing the atom apart. The result? A perfectly stable orbit. Mandatory electromagnetic equilibrium. The atom literally stays propped open by its own internal magnetic repulsion. What's highly effective about viewing the atom through this lens is how it resolves several physical requirements all at once. These classical mechanics explain why electrons in wide outer orbits must have such high velocities. I mean, they absolutely need that kinetic speed to generate enough magnetic pushback against the electrostatic pull. It elegantly neutralizes mass-velocity products, and the magnetic torques naturally enforce angular stability. And it accomplishes all of this without invoking any extra hypothetical particles. Now, to be clear, the source material carefully acknowledges that classical models do have their limits. Eventually, at the strictest scales, you absolutely need quantum electrodynamics, QED, to deal with phenomena like photons mediating interactions. But as a bridging framework, it provides some truly profound mechanical insight, which leaves us with a truly profound thought to end on. If the exact same rules that govern two copper wires on a 19th century lab bench can effectively describe the structural integrity of the atom, we have to ask ourselves, can classical electromagnetism fundamentally rewrite our understanding of the quantum world? Will these foundational laws from Ampere and Lorentz inspire total reinterpretations of nuclear physics in the future? It's a spectacular reminder that sometimes, to untangle the most complex mysteries of the microscopic universe, we just need to look at the macroscopic rules we've known all along. Thank you so much for joining me for this explainer, and remember, keep questioning everything.